Today we'll be talking about group 17 or halogens. Discuss about the color of halogens going down the group. The color of halogens gets darker going down the group. Fluorine is a very pale yellow gas, chlorine is a yellow-green gas, bromine is a red-brown liquid, and iodine is a black solid, but it can easily sublimate into dark purple vapor when we heat it up.
As you go down the group, the size of the atom also increases, which will also lead to an increase in the number of electrons. As the size increases, more electrons will be present, and thus there's a higher number of induced dipole attractions, so the melting point and the boiling point will be higher. Therefore, elements further down the group are in solid form.
Volatility of halogens going down the group will decrease. This because the melting point and boiling point increases. Furthermore, the most volatile halogen is the one with the lower boiling point, aka fluorine, and therefore it can be changed into gas easily. The least volatile would be iodine.
The size of each subsequent halogen atom will increase down the group. This is because there's a greater number of shells. Hence, there's a greater distance between an atom's nucleus and the electrons on its outer shell. Thus, its ability to gain electrons is harder, as the nuclear attraction is also shielded by the increasing number of quantum shells. Fluorine atoms can gain an electron to form a negative 1 ion much easier than iodine atoms. Hence, reactivity decreases down the group and reactions become less vigorous down the group.
So let's talk about electronegativity going down the group. Okay, first of all, we have to explain what is electronegativity. Electronegativity is like the ability of the nucleus of an atom to attract the bonding pair of that they share with another atom. So let's try to represent this in a simpler way. So pretend this is an atom, and pretend this is another atom. This is the bonding pair. So if you see, if this gets close enough, it's going to steal away this bonding pair. So we can try to put this in terms of how we can look at the halogens. So going down the group, electronegativity decreases due to the increase in the radius of the halide atom and increased amount of shielding the outer electrons of the halide atom experience. These two factors outweigh the increase in nuclear charge, and thus it's harder for the halide atom to attract a bonding pair of electrons. Thus, the electronegativity decreases down the group.
Bromine reacts with sodium iodide to form sodium bromide and iodine. This is because bromine is more reactive than iodine, hence it displaces I to form NaBr and I2. Halogens are very soluble in organic solvents like cyclohexane, but is insoluble in water. So they will form layers. Iodine will form a purple layer, bromine will form an orange layer, while chlorine will form a very pale green layer.
As you go down the group, the reaction will get less vigorous as the reactivity decreases. As you can see from the table, when hydrogen reacts with fluorine, the reactivity will be explosive even when it is cool and dark. With chlorine, it is only explosive with bromine slowly on heating and with iodine equilibrium mixture.
Going down the group, hydrogen halides become less thermally stable. This is because when you go down the group, the size of each consecutive atom will increase. So meaning like it'll slowly increase, and get bigger. So the bond line between a hydrogen atom and a halogen atom also increases. Thus, it'll be easier to break the bonds and less bond energy will be needed to break them. More thermally stable halides require more energy to break them. This is also known as hydrogen fluoride.
Next, how can we test the halide ions? First, we can add dilute HNO3 and AgNO3. The silver halides are insoluble. The precipitates formed will be AgCl, they are white, cream AgBr, and yellow AgI. Next, if you have trouble differentiating the colors, you can also add dilute and concentrated ammonia. For AgCl, it will dissolve in both dilute and concentrated ammonia. AgBr will only dissolve in concentrated ammonia, while AgI will not dissolve in any of those.
Okay, so this is a common reaction between sodium halides and concentrated sulfuric acid to form hydrogen halide. So let's see here. Sodium chloride plus concentrated H2SO4 can react to form sodium bisulfate and hydrogen chloride gas. This reaction cannot be used to prepare HBr and HI. So why, you might ask that? So If you can see, concentrated sulfuric acid is a very strong oxidizing agent. So when HPR and HI are formed in this reaction, they will be oxidized by this H2SO4 and form other products. So this will be discussed in the next number, but you might be wondering, why is HCl not oxidized? So H2SO4 has its limits. It may be a strong oxidizing agent, but it's not strong enough to oxidize HCl. So let's talk about those reactions.
The following reactions are done in a fume hood due to the production of toxic gases, as HI and HBr can form acids. NaCl reacts with sulfuric acid to form sodium bisulfate and hydrogen chloride. NaBr reacts with sulfuric acid to form sodium bisulfate and HBr, which then further reacts with sulfuric acid to form bromine, reddish brown gas, SO2, and H2O.
The other reactions are sodium iodide and sulfuric acid will form sodium bisulfate and hydrogen iodide. Hydrogen iodide and sulfuric acid will have three different types of reactions. The first one is when 2Hi plus H2SO4 will form I2 plus SO2 plus 2H2O. Second one is 6Hi plus H2SO4 will form 3I2 plus S plus 4H2O. The last one is 8Hi plus H2SO4 will become 4I2 plus H2S and 4H2O.
Now, what can we observe from the above reactions? Well, from the second reaction, this one, 6Hi will react with concentrated sulfuric acid to produce 3I2 and sulfur. Sulfur will be a yellow solid, and for a back 8 smell, it will be produced from the third reaction where 8Hi will react with concentrated sulfuric acid to form 4I2 and hydrogen sulfide, which I said earlier will produce back 8 smell. For the first reaction, 2Hi will react with concentrated sulfuric acid to form iodine, which is a purple vapor.
So let's talk about disproportionation reactions. So what are disproportionation reactions? It's a reaction in which one element or more will become both oxidized and reduced. So let's look at chlorine here. So chlorine in a cold alkali, the condition is 15 degrees Celsius. The equation should be chlorine Cl2 plus 2NaOH, 15 degrees Celsius. That is very important. It has to be 15 degrees Celsius. React to form NaCl plus sodium hypochlorite and water.
What about in hot alkali? The condition is hot concentrated NaOH in 70 degrees Celsius. The reaction is 3Cl2 plus 6NaOH. It forms 5NaCl plus NaClO3 and 3H2O. For both reactions, chlorine is both reduced and oxidized, so they undergo disproportionation reactions. Thank you.
Oh, sorry. If we can look at the reaction for the first one, Cl2 plus 2NaOH plus becomes NaCl plus NaClO. If you can look closely, if you can figure out the oxidation states, you can notice that NaCl, chlorine will have an oxidation state of -1, and NaClO, chlorine will have an oxidation state of +1. So yeah, you can see that one of them loses an electron and one of them gains an electron. Okay, thank you.